Hello, welcome everyone to the AI and Big Data in Finance webinar. We are delighted to have two fantastic speakers today. So we have Semyon Malamud from Swiss Institute. He'll present his paper on APT or AIPT, the surprising dominance of large factor models. And then we have Paul Schneider from University of Lugano, who will discuss this paper. So the structure is we have 30 minutes for the presentation and then 20 minutes for the discussion, and then we open the floor for questions. If you have questions, please submit it under the Q&A. This presentation is being recorded. After this talk, we'll move to the unrecorded portion, and whoever stays will continue. So Semyon, please go ahead.
Thank you, Serhiy. Thank you, everyone, for inviting me. It's a great pleasure to be here to do this presentation. Some of you have already seen different versions of this presentation. In particular, this paper used to have a different title. Okay, so the title of the paper is APT or AIPT, the surprising dominance of large factor models. It's a joint work with Antoine Didisheim, who's now at the University of Melbourne, Barry Kay and Brian Kelly, who are at Yale, well, and myself. And so, as you can see here, you see large factor models. You can see a clear allusion to large language models, and or more generally to these big models that we observe today that sort of dominate the world of machine learning. And the most important observation about these models is that they're large. They have a very, very large number of parameters, and these models work really, really well. Right? I mean, and so they kind of clash with the principle of parsimony, which largely dominates the economic way of thinking. This is how we were all trained. We were trained to build really small parsimonious models, attempting to build those models so that they can explain reality as we observe it in the most parsimonious way. And as we know, like the large machine learning models today, they're huge. GPT-4, for example, has approximately 2 trillion parameters, right? I mean, so it's kind of absurd if you think about it. How can you even train models like that? And how is it that they don't badly overfit the data? How is it that they sort of work out of sample, whatever you define it for large language models? And you observe it everywhere. You observe it in image recognition, you observe it in audio recognition, surveillance software that various governments around the world are using today. They all use the gigantic models, and they're very successful. They work out of sample. Right? So furthermore, it seems that human beings, they sort of do the same. All of us, even when we have very little number of observations, we attempt to build these very complex models of the world, finding causality and finding sort of features that we observe that we use to explain the data. So it seems that our brains are also designed to build very large models with a lot of parameters based on very few observations, which is sort of consistent with what machine learning is doing today. And so here, what's happening now in finance, similar discoveries are happening. Many of the panelists today actually have papers that provide empirical and theoretical evidence that this is the case, that you can build big machine learning models with a lot of parameters. They actually work out of sample in explaining cross-sectional stock returns. And we have this recent paper joined with Brian Kelly and his student Kanyin Zhou, which is now published in GF, where we show under some technical conditions. Remember, as always, any theoretical result always comes in this parenthesis. Under technical conditions, you can show that actually out of sample performance of simple machine learning models, they actually increase in the number of parameters. So if you want to maximize out of sample performance, you should just push the number of parameters to infinity. And here, of course, you can ask, where do you get those signals? Where do you get infinitely many signals? And so here in those models, what you do is you can have maybe a small number of actual signals that matter, I don't know, stock characteristics, but you can build nonlinear transformations of those characteristics. And this is how you can saturate, you can increase the number of characteristics as much as you wish. And in fact, you will say, well, but many of those characteristics will be kind of very noisy and perhaps not very informative. Well, actually, interestingly enough, Andy Noy here, who is here today, he actually has a recent beautiful paper that shows that noise is not even a problem. And in fact, you can maybe even should add noise to the list of your characteristics. They actually improve performance out of sample, right? I mean, so these are kind of really interesting results. And usually in the classical machine learning problems, you think about prediction problems. Let's say you have an image of cat or dog, and you want to predict this is going to be a cat or a dog based on the pixels that you observe. And in asset pricing, it's not so much about prediction, but about constructing the stochastic discount factor. It is a related problem, but not exactly the same. And in the world of asset pricing, the doctrine of parsimony is still there, and it is represented by this APT, right? Arbitrage pricing theory, developed by Stephen Ross about 40 years ago, 50 years ago. And the idea is that under the technical conditions of APT, the stochastic discount factor should be parsimonious. Namely, only few factors should matter, and then the rest should be relevant. And so this paper, we introduced this thing that we call AIPT, cool marketing tool. Just a play of words, right? The AIPT is artificial intelligence pricing models. And the idea is that contrary to APT, instead of trying to find a few factors that explain the SDF, we build a very, very large number of factors, right? I mean, and so here really we're alluding to this idea that modern artificial intelligence models, they have astronomical numbers of features, of factors, if you want, that they use to explain the data. And so what we prove mathematically is that the performance of portfolio of the SDF is increasing in model complexity, defined as the number of parameters, achieving higher Sharpe ratio, smaller pricing errors. And we find very strong empirical support for the theory. And for those of you who have theoretical mind, the key technical tool that we use is this thing it's called random matrix theory. Basically a special area of mathematics that allows you to sort of run regressions with very high dimensional methods. As you probably all know, whenever you want to run some sort of regression or even gradient descent is just a glorified form of nonlinear regression. You're forced always, sometimes explicitly, sometimes implicitly, to deal with very high dimensional methods, some sort of covariance methods of a sort. And describing the behavior of these methods requires this special area of mathematics called random matrix theory. I'll talk a little bit about it later. So let me show you a beautiful picture that we now think might be one of the most important pictures in the latest version of the paper. So what happens in this world? So think about the world where you have, I don't know, 300 monthly observations, or maybe 600 monthly observations. That would be a typical stock characteristic data set, maybe 60 years of data or something like that, where we have enough characteristics, compustat, CRISP, you name it. So, okay, so you have this about 600 monthly observations, and you want to build, I don't know, 10,000 nonlinear stock characteristics. You take standard characteristics and you pass them through some kind of nonlinear transformations. Okay. And so question is, you have now, and now you can use these few thousand characteristics to build a bunch of factors. Okay, standard like asset price and empirics is called characteristic managed portfolio. Okay, so I'm going to build those. So now I have a few thousand of these factors. And so APT will tell me, well, sure, you have those few thousand factors, but most of them don't matter. It's just kind of noise, so they don't really have high Sharpe ratios. How do you get rid of those? Well, you do a PCA, right? So you can do eigenvalue decomposition of the covariance matrix. You take your factors, build the covariance matrix, look at its eigenvalue distribution, and pick the few largest eigenvalues, right? And usually we detect the factor structure, we detect the fact that we're in the world of APT by looking at the eigenvalue distribution and see, look, there are a few large eigenvalues and the bunch is like noise, and we just ignore them. So here's what I'm going to do. I'm going to do a simulation. I'm going to build a few thousand factors, okay, simulate them. I'm going to simulate one set of factors where the true unobservable covariance matrix of those factors has a factor structure. And that's what I call APT world. So the true APT is the orange line. And I build another set of factors where APT fails. So basically, all of them, basically, I'm going to assume that the true covariance matrix is identity. Okay, so you can see that the orange line here goes very steeply up and then it's flat. It's just an illustration of the fact that there are just few eigenvalues that matter and the rest is close to zero. And the green line, it's a straight line and linear because all eigenvalues are equal to 1. Okay, and now I'm going to take the simulations, two different simulations, commonly for drastically different sort of economic structures, and I'm going to look at the empirical eigenvalue distribution. And that's going to be the blue, okay, so what you see here is the blue line is actual empirical realized eigenvalue distribution that we observe when we use this machine learning methodology that described in the paper, okay? And the purple line, and actually there is a red line which is behind it, but you can't see it because they are identical. So the purple and the red line are simulated eigenvalue distributions coming from these two completely different simulations. One where AIPT holds, another one where AIPT does not hold at all. Okay, and so the striking observation you see is that the red and the purple line coincide, and they are very, very similar to the blue line. So what it means is that in the world of complexity, if you just look at the empirical eigenvalue structures, you can't disentangle, you can't distinguish whether you are in the world of APT or you are in the world of this, what we call AIPT. Okay? This is a general kind of perhaps intuitive, perhaps counterintuitive feature of high dimensional models, of these big machine learning models, that when you try to learn something and you have, I don't know, 600 observations and you're trying to estimate a few thousand parameters, let's say you're trying to estimate weights or a few thousand factors in your SDF, right? You can't do it. You can't estimate 10,000 weights with 600 observations, okay? And so what happens is that you introduce so much noise into your observations that basically you can't disentangle models anymore. And this is really, really an important insight, that given the complexity of the true structure of the world, there's just there are many things that you just can't learn by observing because you don't have enough data. If we had a few billion of years of observations, then eventually the red and the blue line would diverge and we would figure out what it is. But we might live a few billion as a civilization, but none of us will unfortunately see. Okay. So here's another beautiful experiment. So you ask yourself, okay, so you're trying to estimate. So suppose you're trying to estimate a few thousand parameters with just a few observations. How realistic it is? Can you actually do it? And the answer is that actually most of the time you can't. So here's a beautiful simulation that I always, when I teach my machine learning class, I always tell my students, this is how you should start thinking about these things. Do a simulation. So you pick a nonlinear function. I'm going to call it W of X. Okay, and what I want is that the input data D has a sufficiently high dimension. And high, let's say 5. So 5 is actually pretty high dimension. Okay, and you're gonna simulate this function. You're gonna simulate a few hundred observations, and you wanna generate labels Y equal W as there's no noise. Okay, so in principle, signal to noise ratio in this simulated world is infinite. There's no noise. So in principle, with enough observations, you should be able to learn what your true function W is. It turns out that in a typical simulation, typical meaning is a complicated philosophical question, what typical means. Because typical means a typical human being, I don't know what it is, but most human beings I have talked to, my students or other students I have talked to, right? They come up with W functions that are not learnable in finite samples. Okay, this is really striking kind of discovery when you see it the first time. You know there is no noise in the data. You know that your labels are exactly described by the features, okay? But if the nature of the data is sufficiently nonlinear, you just can't learn. So given this result, the fact that in the world of finance, where the world is arguably highly non-stationary and there are huge amounts of noise in the data, the fact that we can build machine learning models that are tremendously complex and that actually work out of sample, where we actually achieve a positive R squared, it's in prediction problems, we're talking about R squared of like 0.5%, maybe 1% at monthly horizon. You could argue it's ridiculously low, but whenever you argue it's ridiculously low, go to this slide and think about it, that in a world where you have no noise, you can actually get an out of sample R squared of 0. So 1% in the world of asset pricing is actually tremendously high. It's telling us that somehow the true structure of financial markets is learnable with the particular machine learning methodologies that we as biological civilizations have developed over the last few decades. And this is really striking. It means that structure, that this true hidden structure of the stock market that we're trying to learn in the world of asset pricing, it's special. There's something special about the structure. And it's not just about the pricing. If you want to push these philosophical allusions further, you could think about images, same, or even human language, where you could say, oh, 2 trillion parameters is a lot, but actually it's not even a lot. And the number of observations on which, let's say, GPT was trained is ridiculously small. If you think about the true complexity of the data. And this is striking because it tells you that somehow everything we observe in this world, language, images, videos, audio structures, whatever type of data we observe, they have structure there. They have mathematical structures that are learnable with relatively simple mathematical algorithms that we as civilizations have come up over the last couple of years. Okay. So let me show you another beautiful example. So basically, I see the time running out of time. So you can take very simple momentum signals, and then you can find that these momentum signals, many of you know it, basically momentum stopped working after the financial crisis, okay? And then if you push these momentum signals through a very simple, this machine learning algorithm, it works, okay? The striking thing is that this is completely out of sample. And so I trained my machine learning models in like 70s and 80s and then 60s, okay? And I tested post 1990s, okay? And it works, and there is no like alpha erosion over time. So what it means is that is not only that there is some sort of nonlinearity in the data that is learnable in finite samples, which by itself is remarkable. Remember the slide in the simulation example. But it means that this nonlinear structure is stationary, is stable over time, or at least some parts of it. Okay? So whatever nonlinearities were there in the stock market in the 60s and 70s and 80s, and the model learned them, out of sample in the 90s and 2000, and even now after COVID, they still work. And they work sort of equally well. And that is kind of striking. It tells you that there are some sorts of universal nonlinear patterns in the data that are there. And this really also gives us a lot of hope as people who do machine learning and asset pricing, because it means like we're doing something like really important. Okay. So normally, if you start thinking how human beings learn and how we build machine learning models, it almost always comes down to this very important philosophical concept, which is called inductive bias. So, okay, so inductive bias is just sets of assumptions that the learning algorithm uses to make predictions or generalize beyond given training data. And the findings that I discussed above, which is basically big models work, suggest that we should reconsider the inductive bias notion and the principle of parsimony. Okay, so principle of parsimony is one particular inductive bias. It's a successful bias. As a profession, the economists, we went quite far with this inductive bias, but now it's sort of the time to reconsider it. And the new inductive bias says complex models seem to explain stock market data better. So why is this important? Why is this moving to this new inductive bias? Well, it raises three fundamental questions, in my opinion. The first one is, what do these complex statistical models actually learn? What does this question even mean? Okay, let's think about it. Remember, I gave you this example where you have 600 observations, and I don't know, you're trying to estimate 10,000 coefficients. There's no way you can estimate those 10,000 coefficients with 600 observations. You would at least need, I don't know, a few million observations. But what is it that you learn? It turns out that this question can be answered with modern mathematical techniques. And what you can show is the following remarkable result. My mind has converged, so I'll not show you much, but rather tell you about some sort of really deep philosophical aspects. And if you're curious, I'll encourage you to read the paper. So you can prove the following remarkable result. So every machine learning model that is this over-parameterized, so that means it has more parameters than observations on which you train it, it learns a projection of the true nature of reality, or whatever, the true nonlinear function that you're trying to learn, on some kind of a manifold. And the dimension of this manifold is actually always smaller than the number of observations. Okay? Or smaller than or equal to. And this really raises a very interesting, very important point, a point about which human beings have been thinking for a very, very long time. And the most famous one is Plato, the famous Greek philosopher. He lived more than 2,000 years ago. And so he introduced this very beautiful allegory of the so-called Plato's cave. So what is Plato's cave about? Plato was arguing that we are limited by our senses, etc. We can't really see the true nature of reality. And then what we actually see is that we see shadows of this reality on the walls of the cave in which we're kind of locked with the chains to the floor. Okay. And so today, finally, thanks to the development of machine learning, we can actually make this idea of Plato rigorous. Okay. So think about the true nonlinear structure, let's say, of financial market that we're trying to learn. Think about it being some sort of a complex three-dimensional object. And every new machine learning we build, every new neural network, every new learning algorithm, every new gradient descent algorithm is like building a different wall in the Plato's cave. Okay, and then basically what we do, we project this body on this wall. We look at it and say, oh, that's interesting. We discovered something new. In principle, these walls can be completely orthogonal, in which case the projections on those walls will have nothing to do with each other. And so me and, I don't know, Andy, we will argue. I will say, look, my projection on the wall is telling me this. And Andy will say, no, I have a different machine learning model. And it's telling me completely different things. But in fact, if the nature of this function is very nonlinear, very high dimensional, well, every wall will give a different view, right? Because you just project. Okay, so that's one interesting question is, what do this projection look like? And what is it we are projecting upon? Okay, so that's question number one. The question number two, why do they work so well? Remember, I told you the fact that we're getting R squared of 1% out of sample is actually striking, okay? So it's telling us something about the nature of the function that actually describes financial markets. In particular, you can sort of prove that this means that the true nature of this function is smooth, okay? That the function that describes market is relatively smooth in certain potentially that can be made rigorous mathematical sense. So this is actually striking because why should it be smooth? Why doesn't have too many kinks or some kind of jumps or discontinuities? Okay. And the third question, which I particularly as a theorist is extremely interesting, I'm actually now writing a paper with Brian and then some other PhD students. What happens in equilibrium if agents use complex models? Why is this question of fundamental importance? Well, think about it. Thanks to the beautiful work of Serhiy and Marcos and Andy and Svetlana and all the people, and Will, all the people present today, and many other people, right? We kind of have convinced a large fraction of academics and practitioners that machine learning works, okay? So and practitioners kind of knew it probably already to some extent, but now they're sort of more convinced. So now imagine we live in the world where a lot of economic agents have realized that using complex models with a lot of parameters works well, right? In the sense that they maximize the utility out of sample. If you want to maximize the utility, you should use complex models. Economists, they may complain and say, oh, I don't understand, it's not interpretable, what does it mean, it's a black box. But if I'm a human agent who is maximizing utility, I don't care. If I know for sure that out of sample, I maximize my utility by running complex models, I'm gonna do it because I'm not, I'm not an economist, I just want to make a lot of money. Okay. So once you admit that, you realize, okay, we need to understand what will happen. And the problem is that all these people will build these gigantic models. And remember the Plato's cave example. So they're going to start projecting their reality on different walls and in this Plato's cave, right? And it turns out that you can use this thing. Remember, I mentioned random matrix theory. You can use random matrix theory to show that any kind of agent doing this will introduce very specific universal types of biases in the way they respond to the data, in the way they learn, okay? These biases can be described using this whatever random matrix theory, and they are universal in the sense that they don't. Some of these biases do not depend on the fine structure of the data. So no matter what the data is, there will be particular biases emerging. Okay, and these biases, because these are equilibrium models, they will impact equilibrium prices, and in particular, they will impact the way information gets incorporated into prices. And in this world of high-dimensional learning, the striking things can happen. As an example, imagine that the true nature of the world involves learning a billion parameters. So to really learn the truth, you need a few trillion years of history. You probably won't have them ever because the universe is not supposed to live that long. So that means that you will never learn the truth. And then in this severely complex sort of environment, you can actually show that prices will never absorb information because people will be just lost because they will not be able to figure out which signal actually matters, okay? And this will lead to very specific sort of, again, sort of universal predictions driven by this thing called universality in the mathematics theory, which again is about the fact that certain objects in this high-dimensional world, that they become universal, they do not depend on the true nature of the underlying data generating process, okay? So this is sort of, yeah, this is the big picture. I hope I wake curiosity. In some of you, let me now quickly remind you what we're doing here. So we're building this SDF, which is basically we're trying to build conditionally efficient portfolio, right? So what you will see here, equation one, conditional expectation of my returns and conditional covariance metrics. And so we simplify it by building these characteristic managed portfolios, okay? And then basically instead of building conditionally efficient portfolio, I build my characteristic managed portfolios, and then I build unconditionally efficient but of this characteristic managed portfolio. So in a way, I take conditional information, which is in characteristics, I embed it into this thing I call factors, these characteristic managed portfolios, and then I use them in an unconditional fashion. interestingly enough, we have a theorem that says that under some technical conditions, this is the right thing to do, meaning the unconditional efficient portfolio of factors achieves the same Sharpe ratio as the conditionally efficient portfolio of stocks. Okay, again, the fact that we're in this high complexity world, it turns out to be very important. Given that I have 5 minutes, I won't really have time to talk about it. And so let me, so what do we do then? So we build this very, very large number of factors, okay, this characteristic managed portfolio. Then we do something completely naive, just build a Markowitz portfolio of this. Just think about it, the dimension of this F is, I don't know, tens of thousands. And we compute this mean based on 600 observations, kind of ridiculous. And we compute this 10,000 dimensional covariance matrix based on 600 observations again, which is also kind of ridiculous, ex ante, right? And then we basically show that this works. Okay, and furthermore, given that I have 5 minutes, I won't have time to talk about it, but you can ask yourself what, well, you're trying to basically get hands on the infeasible efficient portfolio, right? Where you see this is the true expectation. But of course, you can't do it. So what you do, you build feasible versions of it. You just here, in this particular case, we're just taking empirical mean and empirical covariance. And but you can say, well, but probably when T is large, you're going to get approximately the same, but it's not the case. You see that there's this approximation sign and there's a cross sign. If I could, I would have made this cross sign actually red, so to really emphasize it, but I didn't know how to do it. But you can ask yourself, okay, so but how big is the gap? That's actually a tricky question, but you can answer, for example, the following question. Suppose I build this infeasible portfolio, and I want to know, and it would have some expected return. How far is the return of the feasible portfolio from the expected return on the infeasible portfolio? And it turns out that you can answer this question. And the answer is very beautiful. The infeasible portfolio behaves as if it was the feasible portfolio behaves as if it were the infeasible portfolio, but instead of using the reach penalty Z, you use a larger reach penalty, which we call the implicit shrinkage. And beautifully enough, this implicit shrinkage can actually be characterized analytically through this object. Okay, so you look at the empirical covariance matrix and then you start. Okay. So basically what it's telling you that the proof is not completely trivial. It uses this random matrix theory. Okay, but basically what it's telling you is that you can use these mathematical techniques to sort of understand how far you are from this infeasible and essentially unlearnable ground truth. Okay, and the details and exact formulations are in the paper. Again, if you feel curious, please go and read. Okay, so now let me show you some empirics, how we actually implement all this. Well, we take stock characteristics, about 130 of those. Okay, we build a bunch of nonlinear transformations. Here we apply sign to random linear combinations of our data. Okay, so you see we take a random linear combination, then apply this thing which is called nonlinear activation. You will recognize that this actually looks like a neural net. Okay, so we build these features in this hidden layer of the neural net. The fact that we use sign activation is not specific. Results are similar with other activation functions, which actually, by the way, is very surprising and actually telling us a lot about the true nonlinear structure of the data, but I have 2 minutes, so skip that. And then basically, let me show you the main result of the paper. Okay, so empirical. So here's what I'm going to do. I'm going to build a very, very large number of these nonlinear characteristics, okay? And I'm going to plot the out-of-sample Sharpe ratio of my portfolio as a function of this number of characteristics. And what you see here is that as I increase the number of these nonlinear features, the out-of-sample Sharpe ratio, let's look at the orange line, monotonically increases and saturates somewhere around complexity equal to 100. So complexity is defined as the number of these characteristics divided by the number of observations. We use a rolling window of 30 years. So it means that capital T is 360 monthly data. And so complexity of 100 means that capital P is about 36,000. Okay. So if you look at this, picture and you want to make a speculative statement, I don't know, like for a newspaper or something, it's not a correct statement, but it's a speculative statement. It sounds cool and it's cool to tell somebody. Okay. So you could say, this picture means that in order to explain the US stock market, you need 36,000 facts. Okay, this is kind of ridiculous if you think about it, because the number of stocks in my data set is only about a couple of thousand, maybe 2-3 thousand. So how can it be that you need 36,000 factors to explain 3,000 stocks? Well, the reason is that we are trying to explain the conditional structure of the stock returns. Unconditionally, of course, if you have 3,000 stocks, then unconditionally you can have at most 3,000. But conditionally, you can have as many as you wish. And what it depends upon, it depends on whether the vector of conditional expected returns moves a lot over time. To think about it, you have 3,000 stocks, and you take the vector of conditional expected return. There's a 3,000 dimensional vector. And this 3,000 dimensional vector moves over time, over this 300, whatever, something months of observation, enormously. It moves so much so that if you wanted to describe the movements of this enormous 3,000 dimensional vector, you need 36,000 nonlinearity. Okay, and that is basically what this result is about. Okay, I see that I'm out of time. So the conclusion is that there's vertical complexity, and we should use big models, and we should actually also try theoretically to understand what's going on there. And this is going to happen over the next few years as we keep working on this exciting topic. Thank you for your attention.
All right, thank you so much, Semyon. This was very interesting. Paul will now discuss the paper.
Okay, thanks everybody, and thanks to the organizers for giving me the opportunity to discuss this paper. It's a big paper in the sense of what it does and also the page number. I have to admit I didn't look at the all the proofs. So what I'm going to do is, since Semyon gave such a long, let's say, informal introduction, I want to introduce the problem they solve and relate it to what's there already. And I will have like three, let's say, families of questions that I would like to ask, and maybe Semyon can clarify also in the remaining time. So the paper, it evolves around this discount factor projection MT+1. So MT+1 being a discount factor projection, it has to have the property that it prices the returns, in the sense that the expectation of this discount factor times the excess returns is equal to 0. And as Semyon led into the topic, what people have been doing, they have been trying to make this object as low dimensional as possible. There has been research on the question, what happens when the number of assets becomes large? This is an old literature, so it started with the Ross APT, and then very influential papers in the factor literature, Chamberlain, Rothschild, Chamberlain, and Reisman. And there are others, but pretty much this literature, it's still the gold standard. It hasn't changed much. So people have looked at what happens when the assets become large. What this paper does, it looks at the question, what happens if the object becomes more and more complex? So this is on the face of it a very unintuitive approach, as Semyon also mentioned, because we're all trained to make things as simple as possible. And since Semyon didn't have so much time to present his results, I would like to give a short review, like a non-technical summary. So you see under technical conditions, ... the maximum Sharpe ratio discount factor, or the limit thereof, it attains the true unobservable discount factor projection that depends on the true unknown conditional moments. So this is a very, very, very interesting and powerful result. Also a little bit unintuitive, but certainly powerful. So we have to keep in mind that this unobserved maximum Sharpe ratio discount factor, it depends on lots of moments that we have no clue about what they are. But still, with the using complexity, we can still construct an estimator that converges to this solution. So this is one of the first big takeaway that we learned from Semyon's presentation. The other one that is striking is a set of results, again, presented here in a very non-technical way. What happens when the number of factors becomes large. The number of observations in the time series become large. And the ratio of the number of factors and the time series, it converges to a constant, which is strictly greater than zeros. This is a classical setting from high dimensional statistics. And the authors, they provide powerful results for the expectation and the variance of the maximum Sharpe ratio portfolio that comes out of their estimator, the inverse Sharpe ratio, and also the Hansen-Jigenian distance. So very, very powerful results. What I would like to do is to put them a little bit into context and talk a little bit about this very old literature that we have been living with for more than 40 years. So, and I'd like to pick the paper by Chamberlain and Rothschild. So what they wanted to do, they wanted to understand, so when does the APT obtain? And so they had a very, very generic setup where you have gross returns, xi. So each of those has a finite second moment and some mean y. And then they look at the family of portfolios that are square integrable. So they don't assume too much, let's say. The only ingredients that give them all their results are these two statistical arbitrage conditions that also seem very, very reasonable. So when the variance of the portfolio goes to zero, the cost goes to zero, then also the expectation of the price should go to zero in the limit. And they wanted to understand the APT, and to generate the APT results, they had introduced what they refer to as the approximate. They actually called it the K factor structure. I would call it the P factor structure, where on the left-hand side, you have a sequence of covariance matrices. Then you have a part that is attributable to factors. Here you see the Koleski decomposition of the factor variance, and a remainder, which is a sequence of positive semi-definite matrices. Importantly, they have the largest eigenvalue of this remainder bounded from above. So this is like bounded eigenvalue. And then the result is, suppose there is this approximate, this should be a P, sorry, factor structure, and these two statistical arbitrage conditions hold, then even though you don't have assumed so much, you can approximate this the means of the assets with some low dimensional approximation. Sorry, also here I forgot to swap K for P. And so I present this because there are some questions I want to ask that relate to these results. So I would like to discuss some assumptions, and maybe Semyon can tell me whether I understood correctly or not. So they depart from this factor structure in population, where you have on the left-hand side a sequence of returns, a vector that becomes bigger and bigger. Then you have your characteristics, let's say, and then you have your factors, and then you have your residual here. And the assumptions, they are pretty classic. The only one that's maybe a little bit unusual is this one. So the second moment matrix of the factors. So this is not the covariance matrix, but the second moment matrix, namely that's the trace of this sequence of matrices. It's bounded from above by some number. So this is good when you want to approximate stuff, because so the spectrum, it decays very, very quickly of this matrix. But it also has implications. So one of the implications is that the factors, they become asymptotically zero random variables. So because this second moment, it's because the trace is bounded, this means that also the sequence of second moment, it converges to zero. And as a consequence of this, this means also that the means they form like a sequence that of the factors that becomes very, very uninteresting very, very quickly. So I would just like to ask for a kind of interpretation of this setup to relate it. So how is this compatible with the Chamberlain and Rothschild factor structure? That said, I have to say that actually in the paper, there's very little talk about the covariance matrix of the returns, but there's more talk about the covariance matrix of the factors and the residuals. Also a question which I think should be is interesting and should be clarified. So what is the probabilistic structure that is governs the relation between the residuals and these factors? I think so implicitly it is assumed that this covariance, it's for every n, so for every cross section, this is equal to 0. But I'm not sure. Anyway, I'm going to use this assumption in my next question. So if this assumption is made that this covariance, so that the two are orthogonal, then this means that the return covariance matrix, it falls apart into this factor part and this residual part here. And with the assumptions from before, if we look at the trace of this return covariance matrix, and we think of a Chamberlain-Rothschild economy. So when I say Chamberlain-Rothschild economy, I mean there is a nonlinear, sorry, there is an approximate factor structure, which let's say P factor structure, which means the biggest P eigenvalues diverge as the cross section grows. So this means that the trace of this return covariance matrix also diverges. So fine, fair enough. This is also what happens in Chamberlain-Rothschild. What's a little bit interesting is that this factor part, it seems to be bounded. This means that in the limit, you have like almost all the action coming from this idiosyncratic part. So it would be interesting to sort of put the setup more into perspective into the Chamberlain-Rothschild setting, just because this is what everybody has been working with. And so I think that would be really, really interesting. So the next comment, it's maybe not so interesting. It's a technical comment, but nevertheless, there's some, I think there's some interest here. So this is also about the proposition 2 that talks about factor spanning. So the question when a factor portfolio can generate the same maximal Sharpe ratio that the entire cross section can generate. So this is a result that builds upon both the number of assets in the cross section and the factors going to infinity. So there's one thing about traded factor models where the factors themselves are portfolios of the assets. Namely that if we assume, and I think this is a maintained assumption in the paper, that this factor part and the residual part are uncorrelated, and this is, let's say, not the zero matrix, then it cannot be that the covariance matrix of the residual has full rank. And this is something that is assumed in the proof of proposition 2. So again, if I understood the assumptions correctly, if not, maybe you can write them a little bit more comprehensively. But so there's also some new literature, like one of my own projects with Damir about factor spanning with rank diffusion return covariance matrices. So right up the question that Serhiy and Stefan opened up with their influential paper. So the final question, I think I'm not doing so badly on time, is about the setup with random Fourier features. So the paper, it pretty much directly goes to this representation here on the, let's say, on the right-hand side. So these things are called random Fourier features. Every radial kernel, so radial means any kernel that depends just on the difference of the two arguments, it has such a representation. And these omega random variables here are IID realizations drawn from the Fourier transform of whatever the original kernel function is. I think the authors use a Gaussian kernel, and this is also a part which maybe I misunderstood. So that they draw the so-called length scale of the Gaussian kernel from this discrete set here, and simulate the random variables from the Fourier transform of the kernel function. And so complexity here, it refers to P becoming larger and larger. So my question here, since like any set of Fourier features, it has also a limit, which is a kernel function, which you could interpret as like the infinite complexity object. It would be interesting to see like what the empirical results look like if you do it just with the plain kernel rather than the random Fourier features. Okay, so this is pretty much all I have. So this is a very, very ambitious and powerful paper on a very, very interesting set of theoretical questions. It comes with a very large empirical motivation and lots of sensitivity studies and so forth. And they have these two powerful results, which is the sharp ratio question, asymptotic sharp ratio spanning, factor spanning, and also these generalization results. For the future, so since I did this discussion, I have to mention that there are now some really, really well-working non-parametric models available also, both for the conditional distribution. So this can also be fairly high dimensional. And in particular, we also have a new paper on conditional mean and covariance estimators for unbalanced panels. So these may be useful maybe for future studies. This is all I have. Thank you very much. As I said, this is super interesting paper. Very, very, very cool. Thank you very much. It was a pleasure reading it.
Okay, well, thank you so much, Paul. So since we have a few minutes left, Semyon, would you like to use those few minutes to respond to Paul?
Absolutely, with pleasure. Maybe some of the technical questions, why don't we talk in person next time we, whatever, intersect somewhere? Will you be at the annual meeting in Zurich?
So again, sorry, I didn't get that.
Will you be at the annual meeting in Zurich, or maybe you come to Lausanne one of these days? And
yeah, I'm sure there will be plenty of opportunities. Yeah, I'm sure.
But I will respond. Thank you. Thank you, Paul. First of all, thank you. Wonderful discussion, super deep, important points. Most of these points, however, would take me at least an hour to respond. But I will briefly respond to one of them related to the link to Chamberlain and Rothschild. Chamberlain and Rothschild, first of all, they only do unconditional, right? So it's not completely obvious how to link this directly to conditional. But even in the unconditional world, they always assume all these assumptions implicitly, right? Instead of assume that you know the coefficients of the true data generating process. In particular, you know the true means and the true covariance metrics of all stocks or factors in our world. I believe that there are arbitrary opportunities there. Imagine that you have a portfolio of factors. In my world, I have 36,000 factors that sort of matter. Imagine that in my world, there is one portfolio, just one, of 36,000 factors that has a variance of 0 and a mean return of 300% per year. How are you going to find it? How can you find it in finite samples? So in fact, we know that it's basically impossible, or at least, let's say it like this, with the with the machine learning estimators, a relatively small family one that our biological civilization has come up with over the last few decades, where we try to build those, right? There is no one that would be able to find this portfolio. It's very likely it exists, but we don't know how to find it. It's so absorbed by noise that we just don't know where to look for it. You might stumble upon it by luck, but the probability of this is very, very low. Maybe that's what happened in Renaissance technologies. Maybe they just randomly stumbled over 56,000 dimensional vector. It's a joke with a little bit of you know, maybe just stumbled upon this vector, right? But we don't have a technique a universal technique to find it. It will be so absorbed by noise because the variance is so small. So in reality, you don't know the mean returns on the factors. You don't know the true covariance matrix. Remember, I showed you basically the eigenvalue distribution is independent of the true eigenvalue distribution. And so in that sense, unfortunately, the result of Chamberlain and Rothschild is kind of entirely useless. It's a very nice theoretical. It's like in my childhood, there was a jokes about a physicist proving results about an infinite dimensional table in vacuum. It's a fun object to study, but it has no real world analog.
No, it's like the paper is population. It's like
I can't hear you. Sorry.
Developed a benchmark.
You should put down the microphone.
Sorry. So I just said I agree with you. It's a population paper, but there are so many papers that look at the estimation aspect of this. So there is a very, very big literature actually. So I wouldn't, I think, discard it altogether because it's been, I mean, it has substance. I think it would make sense to compare.
But none of those results, all of those, I know very well that literature, but none of those results work in the world where P divided by T is far away from 0, not to talk about P divided by T about 1. None of those results are applicable.
This is what you do. Yeah.
The first statistical results that are powerful, that are useful in this world where P is comparable to T, are due to Marcus and Martin Lethal. That was the first paper that sort of brought machine learning techniques into the world of asset pricing. It was a few years back. And they were the first sort of to introduce this idea that there are, for example, low variance eigenvalues, right? So low variance principal components that are entirely absorbed by noise. You just can't see them. You don't know what's happening there. There's this thing that Marcus in his work calls phase transition. Right? There's a threshold beyond which you just can't see. Okay? And so some of these principal components might have a Sharpe ratio of 1 billion. You don't see them. It's useless. How do you find them?
But I mean, I think it's still a valid benchmark, right? So you have the n asymptotics, at least you have this. Then you have like for a finite set of factors, I think it's fair game, right? So you should, I mean, and you do partially. So you do look at the empirics of the APT also. But I think also in the theory, it's worthwhile. It would be worthwhile comparing to the stuff that's in Chamberlain Rothschild because they really don't assume much. So it's very powerful.
If
I think.
I may
So in particular,
comment here. Sorry, just I don't want to interrupt, but my view on this here, and I mean, Semyon mentioned some of this before, right? The real world has only finite data, and you use theory to approximate finite dimensional data sets. And if you have 1,000 assets and you say, well, that is systematic in the sense it has an eigenvalue of 100, does this mean it grows with the rate of n, the number of assets? Does it grow with the rate of square root of n? Or is it actually finite, but it has just a large proportionality constant? And I don't think you can really, in any finite data set, in a credible way, separate, okay, what rate is it? Or if it's just a large constant, right? So my view is you can derive a statistical model, and the model makes predictions, and then you can see if those predictions are aligned with what you see in the data. But I think I completely agree. Ross-Chamberlain theory is beautiful, but I think from a practical perspective, it's hard to distinguish between different cases here. And another thing, and I mean, we raised this point in our paper with Martin and some work with that Sheng and Stefano later also picked up on the same point. When we talk about what is systematic, we make a choice of what our test or basis assets are. And this is to a large degree arbitrary in the sense that you pick a certain number of stocks, and within those stocks, certain things might look less systematic, but if you add more assets, which were not in your sample, it becomes more systematic, right? So there's a question, I mean, systematic in what type of economic sense? So all what I want to say here is, I think it's great to have this theory. I agree, it's good to discuss it, but from a practical perspective, what does systematic loadings, in the sense it affects a certain rate assets, what does it mean? That's really hard to quantify. Anyways, just
to be fair, I did discuss the the theoretical results. I think those in particular, they should be benchmarked to what's there already, I think. So in particular, the proposition 2, I believe, is this is I think the most contested, maybe.
Okay, let's discuss. Yeah, I think. Thank you, Paul. Let's discuss in person.
Yeah, let me ask you a question. There were like a few questions in the audience, and I'll just abuse my position because some of the questions were related to what I wanted to ask. So there is this question: how do you think about large number of factors, so large P versus like effective, number of effective degrees of freedom? Because even like in my paper, we had the shrinking the cross-section paper. We extended these characteristics to thousands of them by including polynomials. Then I had like kernel trick paper. We had this essentially basically infinite number of them. But then we all do ridge regression on that, right? And if you read Hasty, Tibshirani, Friedman, if you do ridge regression, they basically tell you, well, you should look at the effective number of degrees of freedom, which in that case would be like still small, right? So like, I think like the way I think about it, those are still like low, like you have a low number of factors really effectively, but do you think of it as like large number of factors? So what are your thoughts on that?
Absolutely. So first, regarding the reach penalty, when P goes to infinity, like when you have like 36,000 or something, the Sharpe ratio that you achieve with the best reach penalty, exposed best, coincides with the one that we achieve with the reach. You can see it from the graph that I showed. Now it's not there anymore, but if you look at the graph in the paper, you will see the ridgeless limit, same Sharpe ratio. Reach penalty matters when the complexity is small. Once the complexity is large enough, reach penalty is irrelevant, but for a very deep reason. Remember this theoretical result on which I spent 20 seconds probably during my presentation. Sorry about that. In that theoretical result, I proved that in fact, when P is bigger than T, the model behaves as if there is shrinkage, but it's not the Z, but it's the thing that star, this implicit shrinkage. And even in the ridgeless limit, when Z goes to 0, Z star converges to a large positive number. In fact, this number will explode when P goes to infinity. So when P is infinite, you are shrinking without knowing about it. The model is shrinking for you. It behaves as if you can compute the shrinkage. And very much like in this beautiful work of Marcus and Martin, what happens is that this effective shrinkage defines this phase transition threshold beyond which you can't see. So basically, here's what happens. You have this integral operator kernel, whatever that Paul beautifully described in his discussion. This kernel has eigenfunctions. Those are the true factors, the orthogonal independent factors that drive the cross-section. And basically, only those factors survive that have eigenvalues above the threshold Z star. All the eigenvalues below the star are absorbed by noise, are invisible. And so, in fact, this DF that you construct is described by a finite factor model, and these factors are the true unobservable, I'm going to emphasize it again, the true unobservable eigenfunctions of the kernel integral operator. Now you'll tell me, can't you estimate those factors? And the answer is no. Nobody in the world, as of today, knows how to estimate the true eigenfunctions of this integral operator. And the reason is very deep. The reason is that in order to estimate the true factors, this true finite number of factors, there may be a very small number of those, you need to know the true probability distribution of all stocks and all characteristics jointly. So you're talking about 2,000 stocks, 130 characteristics per stock. So you need a probability distribution on a, well, 2,000 times 100, 2,000 times 130 dimensional space. We do not have techniques as of now to model those probability distributions. This is the reason why we still don't have self-driving cars. This is the reason why large factor models, large language models hallucinate. And so as a human being, I say, look, I know there is this finite number of factors, but I have absolutely no statistical techniques to estimate them. What do? I build 36,000 idiotic, stupid, naive factors, like a monkey throwing darts, hoping that one of my darts will hit. My point is only that this is the most powerful statistical techniques we have so far. As a biological species, the way we have found to tackle these nonlinearities is by throwing darts, by building tens of thousands of factors. It's very likely that in 100 years, our descendants will laugh at us and say, what are you doing? There's only one factor, right? But, well, we don't have this technique so far. It's just a statistical tool.
Thank you. There is actually a lot more questions, but we are running out of time, so we have to end this section, recorded section, and we'll move to an unrecorded section where whoever stays, and we'll just continue this discussion. Before we go there, I just wanted to mention that we will have a next webinar on November 21st. Will be Dmitry Livdan from Berkeley, so please join us on that date. And we'll now move to the unrecorded portion.